Hello, everyone. Good afternoon. Thank you for introducing me. My name is Aleksandra Grzesiek, and I'm affiliated with Wrocław University of Science and Technology. And today, I would like to discuss the topic of testing two-dimensional Gaussian processes with the use of cross-covariance function, empirical cross-covariance function. My presentation is actually based on the publication, which I co-authored together with the other authors mentioned here on the slide, from Wrocław University of Science and Technology and from University of Warsaw. Here's the agenda of my talk. So I'm going to start with the introduction to present you the motivation, the main idea behind the study. Then I will present you some important aspects of the empirical cross-covariance function, which here serves as the foundation of the test we are discussing. Then I will tell you more about the testing procedure, which we propose here. And I will present the two-dimensional Gaussian process, which will be used here as the example in the simulation study we conduct. And at the end, I will present you the results of the analysis of real data that was part of this work. And I will conclude with some final remarks. Let's start. Let me start by highlighting the fact that, of course, Gaussian processes they are crucial in the field of real data analysis. And here we can mention one-dimensional Gaussian processes such as Brownian motion or fractional Brownian motion, which are of course extensively studied in the literature. But also we can find their multidimensional counterparts, which also found many interesting applications in many fields. And in the case of one-dimensional Gaussian processes, what was our inspiration here, there are of course numerous methods for identification, for testing, and here, since we focus on testing, we also focus on quite a new methodology that was designed for one-dimensional Gaussian processes testing. And this methodology is based on time average statistics. And here we can mention, for example, the test based on sample autocovariance function, or the test based on time average mean squared displacement. But there are also other statistics of such type, which can be used for testing in the univariate case. And there is also a paper, which I refer to on the slide, which is a paper on the general methodology, which is based on the so-called quadratic form statistics. And here in our work, we wanted to use this methodology, a similar methodology, but we want to focus on two-dimensional Gaussian processes. Here we propose a methodology that can be seen as the generalization of this test I mentioned for one-dimensional case. So can be seen as a generalization of the test based on autocovariance function. But here, since we are talking about two-dimensional case, we instead of autocovariance, which captures the internal dependence within a one-dimensional process, we use the cross-covariance function, which captures the mutual let's say, dependence between coordinates of two-dimensional process. So this is our goal here. So before we move to the details on the testing procedure, let us focus for a moment on the sample cross-covariance function, because this is crucial here. Let's assume we have a two-dimensional Gaussian process, which is stationary with zero mean vector, and we have certain specified covariance matrix for this process. And now, in this context, the sample cross-covariance function, which is defined on the slide in formula number 1, it can be seen as a natural estimator of the covariance between the random variables x1 of t and x2 of t plus h. So this is our statistic we are interested in. But now we can propose the notation which is given on the slide in formula number 2, and we will refer to this notation as the combined trajectory of this two-dimensional process. And if we use such notation, we can rewrite the formula number 1, so the formula for the sample cross-covariance function, in a slightly different way, and a slightly different formulation, let's say. And this formulation is called the bilinear form. So here we can see that there are two equivalent formulations. One of them involves the trajectory of the coordinates and matrix B, which is specified on the slide, and the second one equivalent involves this combined trajectory and matrix A, which is also defined here. And if we use such formulation, we can get the moment generating function, so the distribution of this statistic of the sample cross-covariance function. And this moment generating function is given on the slide in problem number 6. And it involves the matrix A, which appears in this special form. I presented on the previous slide. We have also the matrix sigma here. So this is a block matrix, and on the main diagonal it has the autocovariance functions of the coordinates of the model, and on the second diagonal we have the cross covariances function. So the cross covariance between first and second and first coordinates. And how do we get this representation? So this moment generating function. So this moment generating function, it follows from the general calculations which are known in the literature, which are the calculations for multivariate Gaussian distributed vectors, and one can find those calculations in the book I refer to. So this is what we know about the statistics. So we know the moment generating function, we know the distribution, and since we know this knowledge about the distribution of the statistic which we are interested in, gives us the possibility to propose a test, a statistical test, and here we consider. So we propose the test, which will operate under the null hypothesis that the trajectory which we analyze forms a trajectory of some theoretical two-dimensional stationary Gaussian process with zero mean vector and some specified covariance matrix. And in this test, we propose as the test statistic, we propose to use this sample cross covariance function with a specified value of the parameter h, which is referred as black parameter. And we reject the null hypothesis formulated in such a way. If the test statistic exhibits extreme behavior, so it's either above an upper critical value, or it falls below a lower critical value, and the acceptance regions of the test can be presented in a way we presented it in formula number 8, where by Q is not the quantize of the corresponding test statistic under the null hypothesis. And of course, we know the distribution, as I mentioned, so we know the acceptance regions, but in fact, In a moment, I will proceed to the simulation study we conducted, and in this simulation study, we use the simulated acceptance region. So actually, we do not have in general those explicit formulas, but we decided to use simulations to somehow evaluate the performance of the model of the test. Sorry. So in a moment we will move to the simulation study. But before that, let us focus for a while on exemplary two-dimensional model, which we consider here. So here we have the two-dimensional fractional Brownian motion. And this two-dimensional fractional Brownian motion, which we consider in the simulation study, it has this representation. It's called stochastic integral representation of two-dimensional fractional Brownian motion. And this model, similar to the model defined in one dimension, it is non-stationary with stationary increments. The coordinates of this model, they are correlated, and this correlation is somehow inherited by the presence of the matrix F, which appears here in formula number 8, and I decided to omit the formulation of F actually here on the slide, but it is given in the language of H1 and H2, Hertz parameters corresponding to coordinates. We have the scale parameters, sigma 1 and sigma 2, which are positive, and we have also the parameter rho, which takes values between -1 and 1, and is responsible for this correlation between coordinates. Actually, there is something more to add about this matrix F, because the matrix F, if the matrix F is positive definite, the process defined in such a way will consist of two vectors of one-dimensional FBMs, which are correlated with this correlation parameter rho. And this condition on F, it depends on the choice of H1, H2, and rho parameters. And in general, the greater is the difference between H1 and H2, an absolute value. The smaller is the maximum value of rho, which can be taken in order for this condition on F to be satisfied. But in the following part of the presentation, we actually do not consider two-dimensional fractional Brownian motion, but we consider the two-dimensional fractional Gaussian noise. So this process is obtained by taking the increments of the process defined in such a way. And the two-dimensional fractional Gaussian noise, it's stationary. And here I also presented the formulas for the cross-covariance function between the coordinates of this process, and so the formulas depend only on the difference between time indexes. And now I will present the details on the simulation study we've conducted here. So we decided to somehow measure the effectiveness of this procedure by applying it to selected two-dimensional processes. Here I will present the results for fractional Gaussian noise, actually. So once again, what do we have here? So in the null hypothesis, we need to assume a certain model, right? So we assume in the null hypothesis, we assume two-dimensional fractional Gaussian noise with rho equal to 0, so independent coordinates, and we will measure the efficiency of the test by calculating the power of the test with respect to rho. So the actual value of rho parameter will be changing from minus 0.9 to 0.9. And we will verify the power of the test with respect to this parameter. As a test statistic, as I mentioned before, we use the sample cross-covariance function, but we can also use this sample cross-covariance function with different values of lag parameters. So we can consider different values of age basically. And so here we decided to check how this parameter influences the power of the test as well. So we have age equal to 0, 1, and so on up to 10. What more, as I mentioned before, the acceptance regions are calculated here by simulations. We simulate the process under the null hypothesis, and also the power of the test is also calculated by simulations. The results will be presented as the so-called carpet plots. So here on the x-axis you have different values of age which were used in the simulation in the test statistic, and on the y-axis you can see different values of actual rho that was considered for the trajectories. And actually, maybe I will explain what do we see here. So we have actually four different plots for 4 different sets of the parameters, and again, each time in the null hypothesis we have rho equal to 0, and by colors we mark the power, the value of the power of the test. So what we can see here. So first of all, we can see that for age equal to 0, the test is the most powerful. So it's almost for all the considered cases. For if we look at the values of rho which are greater than 0, 1 in absolute value, the power will be equal to 1. So we are able to differentiate in 100% of trajectories. And in general, this power of the test will decrease if we consider higher values of age. But of course, this behavior is a bit different in each case, depending on the choice of H1 and H2. But what is also interesting here is on the bottom panels, we can see that even if the actual rho is equal to 0.1 or minus 0.1, so very close to the case of which is in the null hypothesis, we are able to differentiate in the majority of cases. So these are our results for this process. And now I will just mention another analysis that we conducted. So we decided to analyze the real data set to somehow illustrate how this methodology can be applied in the real life problems, let's say. So here we decided to analyze the two-dimensional vector of observations from the financial market. So we have 2 coordinates of this two-dimensional process: the copper price in USD and the exchange rate between USD and PLN. And we know that they are somehow correlated because they are the main risk factors in Polish company KGHM. So we know that there is some relation, and we decided to somehow verify the results which were presented in another paper, which I refer to on the slide. So in this paper, the data was examined in such a way that they were first segmented into 2 regions. And each region corresponds to different, let's say, financial conditions, and they were segmented using the hidden Markov model approach. And then both regimes were analyzed by using two-dimensional autoregressive model of order 1. But there was an assumption that the noise components of this model are not correlated. So rho was assumed to be 0, let's say. And now we would like to somehow verify this, and we decided to use this approach to perform this test we introduced with the null hypothesis that the data indeed correspond to this two-dimensional autoregressive model of order 1 with a specified coefficient matrix, but we decided to check different values of rho. So we verified the values of rho from -1 to 1. So actually we performed here 21 tests, each corresponding to different value of this correlation parameter, of this parameter which is responsible for the correlation between noise components. And here you can see the results of this exercise, let's say. So we have the outcomes which we have for the first regime and for the second regime. So those regimes corresponding to different market conditions. And in the case of regime 1, maybe I will explain what we can see on the plot. So as the red dots, we indicated the value of the test statistic. It's of course the same for each value of rho. And as the blue lines, we indicated the acceptance regions corresponding to each test. And we can see here that in the case of regime 1, the value of the statistic falls into this acceptance region only in the case of rho equal to -0.9, 0.8, 0.7, and in the case of regime 2, it falls into this region only for value of rho equal to -0.5, and so in this case we do not reject the null hypothesis. As I mentioned before, in this paper we refer to, there was an assumption that rho is equal to 0. So this is probably the indication that maybe a deeper analysis of the relation between noise components can give us some additional, in fact, knowledge about this process behind the data we analyze. So this is basically it. I will just conclude in a few words. So here we introduce a new methodology that can be used for testing two-dimensional Gaussian processes. And this methodology is inspired by a similar methodology that is known for the case of univariate processes, and it is based on sample cross-covariance function. And we can get the theoretical properties of this sample cross-covariance if we present this statistic in the so-called bilinear representation, and to check the efficiency of this methodology, we conducted the simulation study that was also supported by the real data analysis, which we hope shows the practical applicability of this procedure we introduced. So thank you very much. Here is the paper the presentation is based on, and the bibliography. Thank you very much.